Hello, my name is Glenn Bevilacqua. I'll present our paper, A Fractional Memory Efficient Approach for Online Continuous Time Influence Maximization. This is work done by my supervisor Lax Lakshman and myself. The input is a graph and an associated diffusion model. The diffusion model specifies how information, product adoptions, or other contagion of interest spread through the network. In this work, we focus on the Continuous Time Event Cascade, or CTIC model. Under the CTIC model, each edge of the graph is associated with an edge length probability distribution, which characterizes how much time it takes for diffusion to occur across the edge. Diffusion occurs up until a specified time horizon, or time limit, t. The set of nodes that can be reached from a source via a path that is less than the time horizon are those that are considered active or influenced. The influence maximization problem then is to find the set of source nodes, also referred to as seeds, subject to a cardinality constraint on the size of the set that yields the highest expected number of influence nodes, where the expectation is over the randomness in the edge lengths. Reverse influence sampling is a powerful technique that is used by state-of-the-art approaches that tackle the influence maximization problem. Reverse influence sampling provides an efficient means to attain an unbiased estimate of the influence spread function, which is sharply hard to compute exactly. The idea was first introduced by Borges and was subsequently refined by Tang et al. The main result of reverse influence sampling is that there exists a distribution over sets of nodes such that the coverage objective function over these sets is equivalent to the influence objective function. To make this a bit more concrete, the way that this distribution can be sampled is that one first draws a random node from the graph, then its corresponding reverse influence sample is the set of nodes that can activate or influence this node in a possible world. A possible world corresponds to one instantiation of all the edge lengths. Existing state-of-the-art approaches to the influence maximization problem first generate and store a huge collection of RI, or reverse influence samples. Then they solve the resulting max K set cover problem, typically via the greedy algorithm. Many works and literature follow this framework. But there's a problem. Storing a large collection of influence samples can become prohibitive. The accuracy with which the RI samples approximate the influence function only improves by processing and storing more RI samples. As such, one may need to sacrifice solution quality simply because more RI samples can't be held in memory. Complicating this is that a diffusion process that results in larger RI samples will clearly exacerbate the memory usage. Under the CTIC model, this corresponds to higher time horizons, which allow diffusion to occur for a longer period of time. Finally, if one wants to select a larger seed set, a more accurate approximation of the influence function is needed, which again means more RI samples are needed. Given this, the goal of this work is to process the RI samples as a stream, and by doing so, completely eliminate the large memory cost associated with storing them. To do this, we need an algorithm that can progressively improve its solution quality. The traditional greedy algorithm is unsuitable for this, as changing earlier selected seed nodes invalidates the nodes that were selected after it. Instead, we focus on optimizing two fractional objectives that extend the influence function. First is the multilinear extension. The multilinear extension treats a fractional solution as a probability distribution over node sets. The second is the fractional relaxation. The fractional relaxation comes from the integer linear program representation of the max K cover problem, and then dropping the integrality constraints. Ideally, we would like to optimize the multilinear extension. This is because it retains the same global optimal solution as the original influence objective function. Unfortunately, it's non-concave, making gradient-based optimization methods incapable of finding its global optima in general. This shouldn't come as a surprise given the known NP hardness of the influence maximization problem. To overcome this, we will also optimize the fractional relaxation. Importantly, this objective is concave, making converging to its global optima tractable. In addition, being a relaxation, its optimal solution upper bounds the optimal solution to the influence maximization objective. Finally, and most importantly, there is a known connection between the fractional relaxation and the multilinear extension. What this essentially says is that if we find the fractional solution that attains high value on the fractional relaxation, it can't be too bad of a solution with respect to the multilinear extension objective. I will now recap the approach using this diagram. The original problem that we wish to solve is influence maximization. The influence objective function is first approximated using reverse influence sampling. This results in a max K cover problem with the special property that the elements that we wish to cover, the reverse influence samples, are streaming, as we do not wish to store them. We use this stream of reverse influence samples to optimize two fractional solutions, one with respect to the fractional relaxation and one with respect to the multilinear extension. If the solution that is being optimized on the fractional relaxation, x, achieves higher value on the multilinear extension than the solution z that is being optimized on the multilinear extension, then z is overwritten by x. This is needed because z could be stuck in a poor local optima. Furthermore, we know that x will be useful for lifting z past poor local optima because of the connection between the multilinear extension objective and the fractional relaxation. To optimize the fractional objectives, we utilize the solution to the linear overestimate. The linear overestimate is constructed from a cumulative of stochastic gradients, where each reverse influence sample produces one stochastic gradient. Solving the linear overestimate amounts to finding the top k entries in the cumulative of stochastic gradients. By constructing the fractional solution from these solutions ensures that the fractional solution will always respect the cardinality constraint. An issue that arises is that we need to keep the computation cost of updating the fractional solutions down. This is because the computation cost of constructing one reverse influence sample may be very cheap, much less than order k. To improve the iteration efficiency, we develop a lazy way of updating the fractional solution that involves writing down to the fractional vector only when the solution to the linear overestimate changes. Doing this, we can reduce the worst-case iteration complexity down to having only logarithmic dependence on k. In practice, it is actually much less than this, to the point that the running time is dominated by the time needed to generate the reverse influence samples. To that end, we also develop a more efficient means of generating influence samples under the CTIC model. Ideally, the construction cost of an influence sample is proportional to its size. However, if the probability of an edge succeeding is low, then we may spend the majority of our time testing edges that do not succeed, and as such, do not add to the influence sample size. The solution that we propose is to test groups of edges instead of each edge independently. The high-level idea is to construct a binary hierarchy of group tests where each test checks whether any edge in the group succeeds. An edge succeeding under the CTIC model means that its edge length is short enough for it to be traversed in time less than that which is remaining until the time horizon is hit. Doing this makes it so that the time complexity of constructing a reverse influence sample only has logarithmic dependence on the edges that do not succeed. This improved influence sample generation can be used to accelerate any of the algorithms that are based on reverse influence sampling. In our experiments, all the algorithms will use this accelerated reverse influence sampling, and we test the effectiveness of this acceleration separately. In the following experiments, we compare our algorithm, FAME, against OPIM. OPIM is a state-of-the-art algorithm for the so-called online processing setting. In this setting, the algorithm's performance metrics such as time, memory, and solution quality are compared with respect to the number of influence samples processed. The first thing to note is that even though FAME does not store the influence samples, the rate at which the solution's expected influence spread improves is comparable to OPIM, which does store the influence samples. This suggests that streaming loses surprisingly little information. Second, the empirical instance guarantee that we're able to certify turns out to be noticeably better than that OPM can provide. This can be attributed to the upper bound on the optimal solution that we attain from the fractional relaxation is empirically tighter than the upper bound that OPM can produce based on the greedy solution. It's also important to note that the empirical guarantees that both algorithms are able to certify exceed the theoretical worst case guarantee by a very large margin. The theoretical worst case guarantee is only around 64%, while the instance guarantees that we see here are over 90%. Finally, there's little running time difference between FAME and OPM, indicating that time needed to generate the influence samples dominates for both of them. As should be expected, OPM's memory grows with the number of samples it processes, while FAME does not. In the conventional setting, a desired solution quality target, epsilon, is specified, and then the time and memory used is measured. Unfortunately, there still can be significant variation in solution quality, i.e. expected spread attained by the return set of nodes, due to how the solution quality target is interpreted by the various algorithms. For this reason, we also compare the expected spread. Our algorithm, FAME, and DSSA generally have comparable expected influence spread, with FAME sometimes being somewhat slower than DSSA. We believe this is primarily due to FAME's stopping criteria likely being more conservative than it needs to be, given that the first sample processing time is comparable. OPMC is substantially faster than both FAME and DSSA, but this comes at the cost of degraded solution quality. The expected spread attained by OPMC's solution is noticeably lower than that of the other approaches. Once again, the memory used by FAME is not impacted by the number of influence samples needed or their size, and as such, its memory usage does not change when the seed set size or the time horizon is increased. This is in stark contrast with DSSA, which uses up to almost all of the available memory at the largest seed set size and time horizon. In conclusion, our proposed algorithm, FAME, completely avoids needing to store influence samples, and as such does not suffer from the memory limitations of existing approaches for influence maximization. The empirical solution quality achieved per influence sample processed is competitive with approaches that store all generated samples. Empirically, we attain a tighter upper bound on the optimal solution than the best existing work. This allows us to provide a tighter empirical quality guarantee. Thank you for your time.